Hi everybody, welcome to Rain's Physics. What I would like to talk to you today about is vibrations and simple harmonic motion. Let's start off by going to vibrations. So vibrations, when we think about vibrations, most everybody knows vibrations and you've seen it in your life, whether it is water vibrating across, or hearing a repeated sound, or your phone buzzing. That's on vibrate. That's what a lot of people come up and they say, hey, yeah, my cell phone is on vibrate. So that's kind of what you think about. But when we look at vibrations, we want to focus on that it is a repeated motion back and forth. And really, it's going to be the source and origin of all waves. Remember, waves propagate energy out. And to do that, it needs to generate a vibration of some kind. And so that's kind of the way we'll look at vibrations and waves. And let's move in and look at the two simple cases that we have. So the first one is going to be repeated motion, this periodic motion of a mass on a spring. Okay, so if I put a mass, attach it to a spring, and I let it oscillate back and forth, like if I hold it and just let it go and let the mass go back and forth, then you will see that it's vibrating. It's going back and forth across an equilibrium point. Let's talk a little bit about what that equilibrium point means. I'm going to give you some information. We're going to talk about mass displacement. That max displacement is going to be from that equilibrium point to the furthest part of way, the furthest it's displaced. So let's take a look at a simulation to see if that'll help. Now, what we can do is if I get rid of that displacement and I come up here and put mass equilibrium, we can see that it goes across this point. And what I want to really show you is when it gets at the very bottom, the furthest it's going to get away from that equilibrium point, or max displacement, they'll have all the force is going to be pulling it back, right? It'll be slowing down to a stop. Much like if you wanted to look at the displacement of this guy. So as it's let go at the very bottom, that is max displacement. And its velocity is going to be 0. And then it's going to come back up. And as it's coming back up, the spring is going to get less tense. And so that means somewhere in the middle, we would have our highest velocity. But then it's going to come to the top and get to a slow point again because the spring is no longer stretched out. Gravity will slow it down to stop. And so that's what we mean by that max displacement. On either side of that equilibrium point, where it's, if I were to put it in there, you can see there, either side of that equilibrium point, the furthest away that it would be would end up being the max, and it would have a force of 0, and it would have a 0 velocity and the max acceleration. Somewhere in the middle, it would have 0 force and 0 acceleration, because that would be the point at which there's the forces of the spring and gravity equal it out. So that's just kind of looking at that simple harmonic motion of a mass on a spring. Now, Hooke's law addresses how the displacement will be when you apply a force to a certain spring constant, how much that displacement will be. And so let's take a look at that now. So here you notice I went ahead and said that at the equilibrium position we would have max velocity and force of 0 and acceleration of 0.